A good moment. All right, so as you know, today we have a seminar. The speakers are going to be our beloved PhD students who are going to basically update us with their progress in the first year of PhD. And the first speaker specifically is going to be Fran Ariza. Yes, also I wanted to apologize for all the technical issues. I don't know exactly what was going on, but apparently it's more or less so yeah.
And don't forget to share screen.
Oh, the share screen. What was this?
The green one.
Ah, of course.
Yes.
Share full screen.
Yes, desktop one probably. Share. And that's it. So people online, can you see the presentation?
Yes.
Perfect.
Yes.
Take it away from
Yes, we can see it.
Okay. I can hear you better than the public. Well, hello everybody. My name is Francisco Arizo. I'm a PhD student here in CEFCA for around 1 year and 2 months, something like that. And I'm going to talk a little bit about the status of the PhD and what I've been working these last months. And well, my thesis title is the study of the environment on galaxy cluster using J+ with different proxies. So well, here we have the index, I am going to talk a little bit. And well, the main thing is what are we going to talk about? The galaxy clusters and which is where are located the galaxy clusters. So we have to know the distribution of galaxies is not universe. It is not uniform in the universe. It has like a cosmic web, like has basically 3 components. Like the clusters is a concentration of galaxies and dark matter. The filaments that are these galaxies and dark matter that links with different clusters, and the voids. There is a lack of dark matter and galaxies. So the main question is what are galaxies made of? Big numbers, between 3 and 5% are galaxies, baryonic matter. To be considered a galaxy cluster, must be the number of galaxies must be around from 100 to 1,000 galaxies. Then we have the intracluster medium that is around 10–12%, and then we have dark matter. Here we have a nice picture of J+ survey, a galaxy cluster in the middle of BCG. This is the most brilliant galaxy of the cluster. We also see the intercluster mean and the intercluster light. So continuing to know what is a galaxy, what are the components, distribution. Here we have a nice picture of galaxy clusters MAC 02723 from JWST. And we have this structure of the galaxy cluster. What is a galaxy cluster? Well, as I said, is a concentration of galaxies that are bounded gravitational in a dark matter hostel. So the main components are the BCG that, as I said before, is the brightest cluster galaxy. That is, if the galaxy cluster is relaxed, is in the center. Then we have the intracluster light that we see this diffuse light that is mainly hot gas in form of plasma, and also stars. And well, of course, if it's a galaxy cluster, we need to have these galaxies. Here in this circle, we can see some galaxies. The main galaxies of this cluster are here, the white ones. And we also can see distorted galaxies that with the distortion of these several galaxies that we can see in the galaxy cluster, we can measure or have an estimation of the mass, of the total mass of the galaxy cluster. So how I'm going to talk first about this, how to observe them. There are in the wavelength range, there are three main approaches that are in X-ray to locate the BCG and the hot plasma, as we can see here with the profile. In the optical to see the distribution of the galaxies, and in the millimeter when the Seldovich effect, that is basically inverse quantum scattering by the photons in the CMB, that when they interact with the hot plasma, with the plasma, the hot gas in the galaxies from the galaxies, that makes a boost of energy and makes a footprint in the CMB, and we can locate it and study these galaxies. So, well, what is this all about? The study of the environment of the galaxy cluster. So we have to know which the main question is how the galaxies evolve from the blue galaxies that are star forming to red galaxies that are quenched. So quenched means simply that the star formation stops. So basically there are three big groups. This is the nature versus nurture. It is basically the mass quenching versus the environment quenching. I'm going to talk a bit very fast about the mass quenching. It's simply related to the secular evolution of the galaxy itself by means of AGNs, galactic winds and supernovae, and we are going to focus more in the environmental quenching. So how these galaxies evolve have been quenched by the interaction with another galaxies. Mainly is about run pressure stripping when the cold gas is stripped from the galaxies, or starvation. That is that the main hot gas of the galaxy is being stripped by the interaction of other galaxies, the intercluster light of the galaxies in a more dense environment, that is the galaxy cluster. So how to study all this? How to approach this study? So what we are doing now, and the main approach of this kind of studies, is to compute the stellar mass function. And the stellar mass function is simply counting galaxies. Don't forget that we are in galaxies, not stars. So this is the stellar mass function of the galaxies. We need to count the galaxies. The main idea, we need to count the galaxies in a volume and being in stellar masses. This must the main idea is easy, but to do it properly is not straightforward, as we were going to see. What is important, the SMF is also exactly observable to study the galaxy evolution, and it's important also to the hydrodynamical simulation, to constrain the hydrodynamical simulation. Here we have the main idea of the SMF. Here in the right we have the Massin et al. SMF, and in the upper part we have the total mass, the total number of galaxies, both population red and blue, and below we have the separation between red and blue. And in the figure on the left we have like how we separate or the main two population of galaxies. We see the red sequence in the upper part, and the blue cloud in the upper part. Later, also we have this green part, but this also galaxies that mainly are going from the red sequence to from the blue sequence to the red sequence when being quenched. So talking about the G+ survey, you all know everybody how it is. It's around it's around 1600 G+ fields observed in 12 optical bands, narrow and wide bands. So we have a lot of sky scenes, so we can make a lot of statistics. So the next step is to download the data. So mainly in this study, we are in a range of redshift between 0.05 and 0.35 because of the limitation of the survey. And when we have downloaded the fluxes, the photo set, and the star class to know which are stars and galaxies. And well, we obtain like about 5 million objects. So now the question is to compute the SMF, we need stellar masses. We don't have it, so we have to compute them. So we have this software very famous, SIGAL, that is simply and very complex. Is to fit with the values of the filters of the fluxes of each filters to make a set fittings, and then we retrieve the stellar masses. We also retrieve the color the rest frame colors and other magnitudes like stellar star formation rates and other things. And here we have some results. We have millions of galaxies. This is two good results. So, well, SIGAL builds models. We have used these 6 models, basically stellar formation history with a starburst delay, stellar formation history delay with a starburst, stellar population from Brussels and Charlotte in 2003, nebula emission, attenuation loss, dust extinction, and model of AGN related. Here we have in the left part a seed of a star forming galaxy with a cutout of it, and in the right part we see a set of a quiescent galaxy that has no formation of stars. So now the question is how we split these two populations in quiescent and star forming. There are several approaches. We have done several approaches also, but the main approach is to make the UVG diagram. But in our case, we have focused in the far UVG diagram because it's more separated both populations. But we are also struggling with that because comparing with the literature, as we will see later, the SMF isn't. We have to. There is like a lack of population of quiescent galaxies. But the thing is that if we use the specific star formation rate to divide, that is used like in leisure, with the separation in -10, we get good results comparing with the literature. So to compute the stellar mass formation, we need to do it quite properly. Before focusing on the galaxy clusters, we have to make a study to see which are the stellar mass function of all the galaxies in this redshift range, to have a look what is going. So we make first the stellar mass formation, the stellar mass function with all the galaxies from J plus in that redshift. And as I said, it's not only like counting galaxies, it's a little bit more complex. The main problem is to avoid or to take into account the Malcolm's bias. This is called, it's simply that the faintest galaxies are only seen in reduced volumes, and the brightest galaxies are seen in all size of volumes. So for this, the normal approach is the Vmax method. This approach is specifically by Pozzetti et al. The algorithm, and to compute the mass completeness. As we can see in the left picture, first we obtain to compute correctly the mass completed, we sort what we can see here, all these galaxies of our study. The x-axis is the redshift, the y-axis is the stellar mass of each galaxy. We see all the distributions, and to correct from to do the Vmax method, we first need to compute the mass completeness. So we sort in magnitude, we select the 20th faintest of in each redshift beam. We determine the mass below lie the 95% of faint objects. This is, I mean, could be a little bit messy, but we have these points in each redshift beam, and the thing is that we fit these points to this different population of star-forming galaxies, quiescents, and all galaxies, to have a look of all of this. The method continues. We have to invert this function, obtain the max redshift of each galaxy at that volume. That is the minimum of the maximum of the redshift of the sample, and the maximum of the redshift of each galaxies in that mass. And well, we get these results. We also have this cumulative histogram to have a look of how is the distribution of the galaxy, of the masses of these galaxies. So we can compute well with all the sample, or we can make different subsamples in around 10.5 with a good completeness. So we have here the first results. We have 5. Okay, perfect. We have here the first results. We have compared with a lot of literature. Here is some examples. We have more comparison with more literature, but we have thought that it would be easier to follow and not be too messy, to compare our sample that is with lines with Mazin et al. 2013. 2013. The question and the difficulty also is to obtain also studies literature with the same redshift of our studies. So we have to manage this. This will be in the thought for future work. So we have here finally the SMF of all J plus in that redshift that we have selected, and we see that basically it is thought that the quiescent galaxies dominate at high masses, and that the star-forming galaxies dominate at low masses. If we compare with the literature, we see that we don't have errors. So the thing is that above 11 and 11.25, the errors are going big. So this separation would be due to that. And finally, here in the left, we have here in the right, we have compare also with the paper of Vilea 2021. It's a study of the SMF with also J plus, but in the very near universe. I think it's 75 megaparsec, something like that. And to compare it and to know which are the limitations. So what we are doing right now is doing the star mass, the SMF, but now in the galaxies from the cluster and the field ones. So here we have a nice picture on where we have the red galaxies are belonging to the cluster galaxy clusters that are cross-matched with red matter. That is a survey of clusters in the red segments. And in the blue parts are the field galaxies that are with a cluster-centric separation between 3 and 4 megaparsecs to know which are the difference and to compare them. And well, this is work in progress. So the thing is that all these methods that we have computed for all the sample with J plus D3 is more complicated than when applied with clusters. So we have to redo a little bit of the code, but to have an idea of what is going on. I know this is basically the summary and the future work, and that's what we're going to continue also to discuss and to know how to separate correctly, to study the environment with different processes like cluster-centric distance, local galaxy density, and in the future with host aromasis. And that's all.
You show that in the previous plot, yeah, here. You're detecting less quiescent galaxies at low masses. Do you think this is a problem of the fitting or it's a problem of
Completeness? Yes,
completeness?
it's a problem of completeness, I think so.
So these works and go deeper, and that's why they.
Yeah.
But
So we're studying
the data one is also J class.
the yes.
In that one, it's yeah, the purple ones are the quiescence of data, and that goes flat.
Yeah, but it's
It's 1 point.
it's
Yeah.
0.01.
Yeah.
Is the worksheet.
Okay. So it's
Yeah.
lower actually.
Yeah, related to that, I was wondering, because it can be due to the redshift range you're considering, you know,
Yeah.
you find the literature and image were more similar to yours.
Yes,
Like, did you check with Red, maybe they do also narrow redshift for their mass function?
the thing is we struggle with that, and we compare with a lot of literature, but it's also that maybe that comparison it was not it would fit it because of the galaxy sample or something like that. But we have a lot of more comparison with literature. This thing is more like what we just compare with Massimudal, but yes, it's a issue to compare with different redshift bins, and we're working on it.
Is there any reason why you stop your selection at 0.35? Why don't you go up to 0.5?
I think it's for the limitation of J plus. So we have the quality of the data, and that redshift is there's a big dispersion when we're trying to separate the red sequence. And
Asking about the limiting redshift, why don't you go below 0.05? You
yeah. Because it's this case of the study, we decided it's at low redshift, but it's not exactly in the local universe. It's like
I do have a couple of questions myself. I'm a complete foreigner to this subject, so please bear with me. So in Seagull,
yeah,
you have to establish some models
yeah.
for the kind of galaxy. So how does it work? You put
Western.
those models, and then Seagull chooses which model is the most suitable for each galaxy, or you have to previously know more or less which one of the models is going to work best.
No, it makes a grade with parameters with this modules that I say, and it retrieves the best set fit with the less chi-square. Something.
All right. So then my question would be like, I guess you have a good reason to choose these models
Hmm.
versus other models.
There are the, well, basically we talk with Juan and it's the most used. The ones to
If one.
Yeah, try to carefully in the.
I don't know.
Yes, well, so some parameters, it doesn't interpolate in the grid. It has some Bayesian estimates for some parameters. But when you pick the best fit model, this is a model, it's not an interpolation.
And then my second question is that I'm a bit puzzled by this sky distribution that you show with the red and blue galaxies that are outside, that are field galaxies. I see a crazy selection effect there. Like, why? So like, I don't understand this. Like the field galaxies are basically
Are
distributed in-
galaxies
Uh-huh.
between 3 and 4 megaparsec from the galactic
Ah.
center of each
I missed the.
at each redshift of the galaxy cluster. So we see different sizes of
There. I
observers.
thought that they were just field galaxies, farther than 3 megaparsec away, and I was puzzled by not seeing like.
The blue ones are, well, we consider that field galaxies or galaxy clusters. They are remote also this all these galaxies that could belong to both clusters and we retrieve only this.
So like the white regions between the clusters, are they also considered field in your method? Because we would assume they are field, right? The ones
For our
between the
solution.
two.
Exactly.
Between these ones, for example.
Yes, or the larger, yeah.
No,
between
because
the-
this would be more than 4
Claro.
megaparsec away. That was my question.
Our definition for field galaxies is
Yeah, this
between
is-
3 and 4
it's
megaparsecs.
Why not infinity?
Do not get contaminated with another cluster, so another galaxies that don't belong without the galaxy cluster.
Well, you already discarded them from the other clusters, right?
No,
But we might be missing clusters, is that you're missing clusters and
I think to account, this is photometric. So if it was spectroscopic redshift, you make it sure that they belong to a cluster and they are not included. But as this is photometric, we try to avoid contamination from other clusters. So yeah, in the middle, we don't have like information. So this is the easiest way, and for the field, we want statistics. So far, this is like a test. 3 to 4 is just to make the first test. The idea would be to do in some concept a cluster-centric distance. So this is kind of picking 2 cluster-centric distance, the 4 and some at 3, 4. But in the future, that will be like a continuous that we will go up to, I don't know, 5, 6, 10 megaparsecs.
So maybe we should call it slices. Maybe if you call it circumcluster. It's interesting.
And related to that, also in the figure where you show the mass versus redshift, there's a very important effect of discretization in the redshift, right? I guess you didn't complete the photosis yourself, but
what?
yeah, in the next figure, in page 14,
This one.
the redshift means the redshift distribution is not complete.
Yeah, it's discrete.
I guess it's for the photosis,
Is the photosynthesis, yes, right?
but first I'm surprised that it's so discretized.
Yeah.
Yeah. And secondly, I wonder.
You will be protected by fluid agreed.
Yeah, no,
More grades.
But that agreed your computational point. I mean, if your uncertainty is going to be like 2%, what is the point of making a much more than that?
So it is some
That
caution
that is
for
different.
presenting.
You can blur them.
It's a bit-
What each of these groups has probability distribution function. I would guess that all of those, in fact, they do have their error one, which in fact is the probability distribution function.
Some last question? Or if not, let's thank, Don Gonzalo. Do you have your presentation?
Yeah, I have
in?
in. Hello everyone, and I'm Sepide Skandarlu. I start my PhD from 15 January of the 2022, and until now I will present for you how much my PhD had progressed. My PhD title isn't about the PSF. And I want to show you why now we are working on a PSF. My PhD title, my thesis title is about the circumgalactic medium in a local universe with J plus and J plus. When I came here, I start working with the J plus on a detection of the galaxies in a crowded region. But the main question is why J plus and why the crowded region? I selected J plus because we have a 56 filter and it's allow us to looking for the photospectral features of the object. And why the crowded region? Because I'm going to looking for the local universe galaxies. The local universe galaxies foreground contaminated by foreground and background object. First of all, we should separate each object from each other, and then looking for the circumgalactic object. If we don't pay attention to this issue, we are going to miss the correct information of the circumgalactic medium. In some cases, it's contaminated by the foreground stars. We cannot study the stellar population of the circumgalactic medium correctly, and even though maybe we consider it mistakenly as a tidal feature object. Due to this, I select the famous cluster in a mini JPass.
Just click on got it.
Yeah,
And got it. And set it and finish.
So sorry for audience. No.
No, it's not your fault.
Why we want to looking for the tidal features, tidal feature object blindly, because as I said before, we have 12 filters in J plus and 56 filters in J plus, and it allows us to blindly looking for the object with the tidal features, because most of the people these days select an object that they know they has a tidal feature and then studied it. But by J plus and J plus, we can prepare a catalog of the most of these objects. And due to this, we want to find a way to automatically separate object with the tidal features from the other object. It has a problem again. Okay, and this is just the proof of concept. I model the galaxy with the same magnitude, and because I want to be as simple and just find a method, I put a ring with different magnitude around this object. It's for me, this is something like the J plus and J plus with a different filter, because we see the extended emission object in different filter with the with different brightness. And then I apply the different threshold and all of these different objects. And I saw the object has a bright tidal feature. The scope of the area above the threshold separate from the other galaxies sooner. And you see, because they are faint and I couldn't detect them very well, the scope is I couldn't separate them accurately. It was just a proof of concept. And then we realized by this method, we can separate stars from galaxies. All of these dotted lines belongs to the galaxies, simulated galaxies by GenoAstro, and the solid lines show us the stars. This method work correctly, and you see we could separate the galaxies from stars. But for these galaxies, because they are unresolved galaxies, we couldn't separate them because they are unresolved galaxies. And we were working on there, but we faced with another problem. What was the problem? This is the simulated galaxies with the tidal features. This paper belongs to the Martin. And after convolving with the PSF, you see in this part, after convolving the PSF, the light of the galaxies comes here. And I should at first build a accurate PSF for our data. Another problem is as you see, this is after adding the noise to the simulated image, and the tidal features are so faint. And in some cases, this is a paper from the Martinez, and in some cases, these tidal features contaminated by bright stars, and it is necessary we subtract the stars from all the images and then looking for the tidal features object. As I said, you see this galaxy is blue. Sorry, this is a blue and this is a red galaxy. If I don't consider the PSF, the light of the PSF don't allow to us to study the stellar population of the tidal feature accurately, because they are mixed together. Okay, now due to this, we decide to construct the extended and non-parametric PSF for whole the J plus and subtract it from each tile. This is a footprint of the J plus DR3. Each of these a small cube show us a tile of the J plus, and each tile has at least 3 different exposure and 12 filters. Because we want to see how PSF change based on the filters, based on the CCD position, based on the exposure, we decide to, for each exposure, each filter, build a different PSF. Please let me show just one of these small tile. This is a common cluster tile. And as I said, each tile at least has 3 different exposure. And I wanted to build for each exposure a different PSF. Because I want to build the extended PSF and I didn't have enough bright star in each tile, we decide to use the exposure were taken 2.5 hours before and after the main tile. Then again, I couldn't use all of these tiles. Why? Because the magnitude of stars are important. If I don't pay attention to this issue and then stack the stars with different magnitude, I will lose the outer part information of the PSF. And due to this, at first we found bright stars, And then based on the magnitude of bright star, I select the star. They were half magnitude fainter than bright star, which are shown by the purple cross in that image. And we build the stem of stars. A stem of stars is the cropping the stars and masking the extra object. But again, we feel faced with another problem. This is the reflection of the mirror, and we couldn't find a reflection of mirror in this project manually, because this is a huge project, and we decided to find a way to automatically mask the reflection of mirror. This is one of the brightest stars. As you see, we don't see any reflection of mirror here. First of all, we divide this star to the 4 different corners, and then we plot the surface brightness of a different angle. And we select the angle has a less signal to noise. In this image, this region has the purple region has a less signal to noise. And then based on this radial profile, we build a 2D radial profile, then subtract it from the main image, and you see all the reflection of the mirror remain on the stem of stars. By noise we detect it, and at the end we mask the reflection of the mirror. Now a stem of the outer part of stars are ready. We stack them together and build the outer part of PSF. This is a radial profile of this PSF. And you see at the center part, we are missing the information of PSF. Why? Due to the nonlinearity and saturated pixel. We need to the other part of PSF. We had enough stars in each tile. We select among the saturated star, we just selected 10 of the brightest of them. And I show here by the red cross. And then we build the stem of them and make a middle part of a PSF. Then you see this is the radial profile of the middle. And then we use the 100 of the non-saturated star for constructing the center part of PSF. In here, you see the surface brightness of the PSF. If I go from the central part of PSF to the outer part, you see the surface brightness gonna change around 15 meg per arc second. And I uniting the different part of PSF in this region, I show by the green and the blue line. And I show it here. And this is the final PSF. This is just one PSF for one tile and one exposure. But in our pipeline, for each exposure and each filter, we have a different PSF. And this is one of the exposure in a J+CR3. And this is the final result after subtracting the PSFs. And this one is the scatter light of all of these stars. And yes, now this tile is ready. I start my PhD thesis and looking for the tidal features object. And I should say that all of this work was based on the Raoul's paper. And I create all of tools for all of this work by myself. During the last year, I had more than 15 commits on GenoAstro, and I wrote this script and this section of the GenoAstro by myself. I wrote this section again in GenoAstro. Recently, we add a new script for obtaining the 0 point, and I debug all of this script. And yes, I wrote one paper by helping the rolling point sign postdoc in SEPCA. Elham Saremi, she is the postdoc in IAC. Samana Raji, she is PhD student in Valladolid. Julia Golini, she is a PhD student at IAC. Zahra Sharbab, she is a PhD student again at IAC. Zohra is postdoc. You saw him, and by helping the Muhammad, and we will submit this paper this month, next week. And this is my paper for the PSF of J+. I wrote the more than 8 pages of this paper, and I will submit it in May, I hope. And yeah, I have a collaboration with the Light Group. I should say that I'm thankful from Ignacio Trujillo. He helped me too much in constructing the extended PSF, and we are collaborating in a lights meeting. And 2 weeks ago, I went to the INT and observed some galaxies by INT with a long exposure. And I will use this data for comparing for my PhD thesis. And I will collaborate with Arrakis, yes. And at the end, this is the timeline of my PhD. As I said, this is the 4 year of my PhD, and each season. And I will publish my first paper and then second paper, and all of this has a stars. It has a star. It's not a priority. It depends on the JPass when it's gonna launch. And yes, and at the end, I will looking for the job for my postdoc. And yeah, it's finished. If you have any question.
Just for the record, it was Javier who stole the license. So, questions?
So it's like a 2-part question. Why do you go to single images over the tile? Like, why do you do the work on the constituent image of the tile? When you go to your slide, you have your tile
In
first,
PSF.
and then you have the 3 individuals. Yes, for the PSF.
Yeah, he this part.
Yeah. So
Yeah.
why did you choose to go on the single exposure instead of the tile? Is the first part, and second, when they are combined, the tile, the 3 individual exposures to make the tile. I'm not sure exactly how it's done, but I presume there is some sort of convolution there. How would that affect the PSF from the individual image to apply it to actually how the tile is combined?
Okay. First, we decide to select a different exposure because we want to see PSF change exposure by exposure or not. But I don't check it yet, but I'm not sure. But if they don't have any difference, I will be stack them together, and for example, stack all of these exposure together and decrease the signal to noise and use it for my building the PSF. But I will check it.
Okay, so you could do that like directly on the tile, which is already combined.
Yeah.
Well, just to add that, once I put an answer, because the ultimate goal of this is JPass. So we want the algorithm to immediately apply to JPass as soon as the first data are sent. And in JPass, the tiles are not so easily correlated to the exposures. So we wanted to design it in a very generic way. So tomorrow when tomorrow hopefully, when JPass starts, yeah, we can just take the same algorithm and run it in there.
Elena?
Yeah, I think it was one of your first slides. You showed a plot where you were trying to separate stars from galaxies.
This one,
Yeah, the next.
yeah.
And I didn't understand very well what are the meaning of the axis and how they use.
Okay, by noisy cell, at first I separate the signal from the noise. Then I apply the different threshold you see here. Different threshold on the on a detection, not on a noise. And here, because the stars are different at the center part, because the stars are so sharp. And we want to just select the maximum of the pixel. That pixel has a maximum value to separating the stars from the galaxies. Because in the maximum pixel, they will show the difference. Because the stars are sharp at the center, we could separate the stars from galaxies. And this is a fraction of the maximum values of the after applying the threshold. And this one is the area, yes, area of this maximum pixel. Pixel has a maximum values.
So it's the fraction with respect to the full.
Yeah, yeah.
When it's half, it's effectively fully to half.
I have one. Maybe you said that and I missed it when I was running. No, the ultimate goal is to study the circumgalactic medium.
Yeah.
Are you interested more in the diffuse stellar light or also in the line emission, and which kind of analysis do you plan to do with that component?
First, I will separate the object with the tidal feature or extended emission or everything from the other. I prepare a catalog for J+ and J+, and then I study on a stellar population of them, the color and everything, and the extended emission.
So you plan to do a LCD fitting? Or
Yeah. And if I will find a interesting object, we will write a proposal for the other telescope, such as Keck, Muse, and then detect it by the.
More questions? Okay. If not, I think we stop here, and then we have the one-to-one with me.
Stop the recording there.
We should wait.